So in this video, Nick and I are going to present the end-to-end principle in network design. So if we look at how a networked application sees the world, it sees something like this. There's one computer running the application, some other computer running the application, and then in the middle, there's the internet. And its abstraction of the internet is that it can send packets. Each node, A and B, can send packets addressed to each other, and the internet somehow magically delivers them from one end to the other end. And all it does, this is all the internet really does. It just forwards these packets along. And so you can ask the question, why doesn't the internet do more than that? Why doesn't the internet help these applications? You know, they're just sending packets, but maybe it's a stupid application. Maybe it could do something much better, and the network could help it do something much better, such as the network could automatically compress data, reducing the capacity needed and therefore increasing the throughput of the application. It could reformat or translate or improve requests. If it realizes that you're requesting an HTML document in an inefficient way, it could reformat the request for you so that you get a better response. Rather than give you the data from the other computer, if it has a cache closer to you, it could just give you the cache data. It could add security. This would be really useful if you're running an application which is insecure. The network could automatically add security. So there's confidentiality and integrity so people can't eavesdrop on what you're doing. There's all kinds of things that the network could possibly do to help you. Right? So you just send simple packets, and then the network does the smart things to make your application work better. So why doesn't it? Or why do we have this model of the internet just forwarding packets?
So an early guiding principle for the inventors and the early pioneers of the internet was to try and create a network that was dumb and minimal, in that it would do the least that it possibly needed to do, and then push as much of the functionality and the intelligence to the edges, as close to the application as possible. And this is what is widely referred to as the end-to-end principle. It's actually been around for many years before the internet, but when the internet came along, this was the biggest application or the biggest use of this principle, and so has become very widely used as a defining principle in many computer systems since.
And so while this principle existed for a long time before the internet, it was really sort of written down and codified in this very seminal paper by Salzer, Reed, and Clark called End-to-End Arguments in System Design. It was published in 1984. This is the end-to-end principle. The function in question can be completely and correctly implemented only with the knowledge and help of the application standing at the endpoints of the communication system. And so the idea is that if I have some piece of application logic or some application function, while the network can possibly help, ultimately the endpoints of that communication have to be responsible for making sure it works correctly. And so the communication system itself, providing that question function as a feature of the communication system itself is not possible. So sometimes the communication layer, like the internet, could help you, could improve performance, but ultimately it has to be up to the endpoints to ensure correctness. They call this line of reasoning the end-to-end argument, that if you want to accomplish some application goal, ultimately that goal must be implemented end-to-end. Something in the middle might help you out, but you can't assume that that will be there, you can't assume that will be correct, and you must have the correctness implemented end-to-end.
So let's take a look at some examples of where the end-to-end principle comes to help us. So the most classic example is file transfer. File transfer, where we are taking a file from one computer and delivering it intact, correctly, in correct order, and to the other end. So what we would hope of the entire end-to-end connection is that file would be delivered correctly, such that every byte at one end is correctly delivered to the other end, in order, such that if any are lost in transit, that they will be retransmitted so that we can be sure that they eventually get that. Now the network, the intervening network, could make sure that the file is transferred to some intermediate point, and then from that intermediate point stored and forwarded along the path. Or on every link along the way, it could make sure that if there is data that's dropped, it could retransmit that data. But what the end-to-end argument says is, even if the intervening network is trying to do that, the only way to ensure that end-to-end that the data is delivered correctly and in order is for the end-to-end to be responsible for it and have the means to both check it and to ensure that any missed data is filled in, any out-of-sequence data is put back in the correct order.
So the original paper actually went into a specific example that the authors encountered with the Multics operating system, which was the sort of the predecessor of Unix, where they had a file transfer protocol which assumed on each hop that had retransmissions, it had reassembly, such that if I want to get the file from A to B and it's traversing these intermediate nodes C and D, these nodes would be responsible for the reliability along each link. And the problem that occurred was that there was some faulty memory in one of these nodes. And so the packets of data were transmitted, say, from A to C. They were transmitted correctly, but then while in C's memory, C corrupted them. And then C forwarded them along, these corrupted pieces of data, and then eventually when the data arrived at B, it had been corrupted. So the file was corrupted, and they lost a great deal of a big chunk of Multics source code because of this. And so the argument, the end-to-end argument, says that while the fact that the A to C link was doing retransmissions and doing reassembly and able to then ensure this reliable transfer from A to C, the actual transfer from A to B requires an end-to-end check. That is, when B receives the data, it should somehow verify with A that the data it received is actually the data that A sent. The network can help by doing retransmissions in the middle, etc., but that help does not obviate A and B from doing the end-to-end check for correctness, because there can be errors within the network. And so another example of this, and this relates to the Multic example, is link reliability. So if I have a set of nodes, say along a route, and so here I have 4 nodes, A, B, C, and D, and I want to ensure perfect reliability from A to D. One question you can ask is that every packet which A sends will arrive at D. One approach is that you could just have each link be perfectly reliable, such that when A sends a packet to B, B either sends an acknowledgement. If A doesn't hear an acknowledgement, it'll retransmit, such that along each link you'll have perfectly reliable transfer. And same will B will do to C, and C will do to D. So now each link has 100% reliability. And you could say, well, since each link is reliable, the overall route is reliable. And so we don't need for A to check with D whether it received all of the data. But so what happens if A sends data to B, B receives it, B acknowledges it, and then B crashes, and that data is lost out of its memory? This link was perfectly reliable. The data was delivered to B, but then B lost it up above the link layer, up above this communication layer. And now suddenly not all the data will be delivered to D. And so the end-to-end principle in this setup is that A needs an end-to-end check that the data actually arrived at D.
And so you can take this example and use it then to think about how the overall system is designed. One could imagine a way in which each link, or a system in which each link was providing that retransmission, and then you did the end-to-end check as well. It then begs the question of, if you're going to do the end-to-end check, should you actually put in the checks and the retransmission on each link along the way? And that's a design choice when the system is being built. And the basic thinking and the idea behind the end-to-end argument is, not only do you need to do it at the ends, but if you are going to put it at the ends, then one can draw the conclusion that you don't need to put it in the middle, therefore simplifying the network that interconnects the endpoints.
And so while the original end-to-end principles described in that seminal paper said that you have to do an end-to-end check, and you can put some stuff in the network if you want to improve things, a general sort of philosophy today in the design of networks is that you should avoid putting things into the network. So if you look at RFC 1958, this is what I like to call sort of the strong end-to-end principle. It's not that you have to do an end-to-end check, or you have to do end-to-end correctness, but rather you should also avoid doing things inside the network. And so RFC 1958 says the network's job is to transmit datagrams as efficiently and flexibly as possible. Everything else should be done at the fringes. This argument that It's not that everything has to be done at the fringes, but in fact the network should do very, very little, if anything, to help. It should just forward datagrams.
So throughout this course, we're going to see lots and lots of examples of how the internet works, why it was designed the way that it was. And you're going to see that there is this general guiding principle in the way that the internet was designed to make the network as simple as possible. However, you're probably going to find yourself wondering on many occasions during this course, and in fact we would encourage you to think of it this way: does the network need to be doing that function? And it's worth thinking critically about this as we go along. So we'll give you some examples. There have been many proposals to introduce link-by-link encryption, in which data along a particular link is secured so that it can't be listened to or interfered with by another user. So a interesting question to ask is, if the network is doing this, and then I still have to do this end-to-end, what is the point in the network? What is the purpose of the network doing this? And so this creates lots of debate and arguments among internet designers and people who are building networking equipment as to whether such a feature or function. And we'll see some examples and some very subtle points as we go. For example, there's a very common desire for the network to replicate packets on our behalf. Imagine that you're listening to or watching broadcast TV over the network. It would be natural to suggest that the network replicate the packets from when they're being transmitted to be received by everyone who's watching that broadcast. And there's a very legitimate question: should the network replicate the packet, or should the sender replicate the packets? And so this is an area of lots of controversy and some great debate over the years. And so we will see that it's a guiding principle that is a very powerful principle, and has served the internet well in keeping it minimal, simple, flexible, and streamlined, although there is a constant vigilance to make sure that it stays that way.
So another good example of this relates to sometimes a network provider has a link that is very, very limited. So they have, say, some backhaul link, and capacity on that link is very limited. And so what they do is they want to take the data that's going over that link. Maybe it's just HTML, so it's ASCII text. ASCII text is very compressible by about a factor of 8 to 1 even. And so if you were to take the data going across that link and compress it, then suddenly you increase the effective capacity of that link, assuming it's, say, mostly HTML traffic, HTTP, by a factor of 8. Now, to do this requires looking inside the packets that are going across the link. You get in a packet that is a certain length, or say a TCP segment, some higher level protocol, you have to actually start peering inside these transport layer segments, layers above which you're supposed to be concerned with at the network, and start changing the packets. And so there are situations where providers do this, but now the code that they have that looks at these TCP segments, that looks at these transport layer chunks of data, makes certain assumptions about the way the transport layer works. And if you try to do something new or slightly different, or something which that code doesn't expect, then everything breaks. So for example, there's one researcher, there's a paper just appeared this year, where you showed how if you start doing things which are perfectly legal under the TCP specification, but which are not commonly what existing TCP stacks do, these kinds of links that are rewriting packets and generating new packets and trying to simulate a link to compress data fail. And so you're doing something which end-to-end should just work. The network shouldn't be looking at your TCP segments, but because it does, it then causes your transport stream to fail.
So up until this point, Phil and I have been talking about some of the technical and architectural aspects of the end-to-end argument. But it turns out some really interesting business and political aspects to this discussion as well. The debate about net neutrality is largely about the following problem. If you are a user at home or in an enterprise who is using the network, and you're using a service or an application that requires data to be delivered to you, for example, you're streaming video, or you're in a voice over IP communication, then the question is, should that data receive better treatment because of the application that you're using, depending on what the application is or where it's coming from, decided by somebody else, so that they can make a decision on your behalf of which data is more important. Because if your connection to the internet is in some way constrained, it doesn't have a sufficient data rate, then it seems reasonable to think that you will identify some traffic as more important than others. So it comes from a sense that if there is a constraint and a bottleneck, then it makes sense to differentiate that traffic. However, the controversy comes from who gets to decide? Who gets to decide that some data is more important than others, and that some data should be delivered more reliably or more quickly than others? And that then enters a very, very complicated economic and political discussion, because it then gets to the point of who controls that connection that we have with the outside world. So it then brings in all sorts of questions and fears about walled gardens and people preventing us from doing things that we want to do, and taking us right into the question of censorship as well. So it's a very, very complex and controversial topic.
So the end-to-end principle might seem like this abstract concept about how you build networks and retransmitting packets, but it has very real implications today with respect to the politics of the internet and the economics of the internet. In fact, in some ways, net neutrality is, at some level, an articulation of the strong end-to-end principle, that the network should just dumbly forward packets. It should not treat different packets differently. It shouldn't treat packets from some application different than any others. Because the network should just be the simple, basic abstraction of delivering packets. And that's one of the arguments for net neutrality. And so it's about the strong end-to-end principle. But of course, people don't completely agree about this. And so there are some people who are strongly in favor of net neutrality. So here are two of the pioneers of the internet, Vint Cerf and Bob Kahn. And so Vint Cerf, testifying before Congress, basically said, hey, allowing these broadband carriers to control what people see and do online, that is to control their packets, make some packets faster or slower, it undermines the basic principles of the internet. In contrast, Bob Kahn says that he's totally opposed to mandating that nothing interesting can happen inside the network. And I think there's sort of this tension, right, about, you imagine you're a service provider, you want to make your service, you're a carrier, you want to make your service better to users, you want to add some optimizations. And there's a concern, by so doing, you're going to prevent future users or existing users from doing new and interesting things. So what actually triggered, the event that really triggered the whole net neutrality debate, and here's an interesting example of the end-to-end principle, should the network be smart or dumb, was when BitTorrent really started to take off. And so it turns out that the way that Comcast, a particular service provider, had constructed its network, nodes in Comcast's network had very large download capacities. So here's the internet. Here's the internet. There was very large download capacity to these nodes, to your machine at your house, and a small upload capacity. So there's an asymmetric capacity. So you could download lots of stuff from the web, but web requests are small. But now the thing is that BitTorrent, just because of the way it works, really tries to get symmetric traffic. So it tries to be big uploads and big downloads. And so what BitTorrent started to do was to completely overload these small upload links in Comcast's network. And from Comcast's standpoint, there are a couple of BitTorrent users who are using BitTorrent, and it is making the internet amazingly slow for all of their other users. Because the other users just want to use the web, but suddenly their web requests take seconds rather than hundreds of milliseconds. And so they were just seeing terrible performance, and they're trying to satisfy the desires of their 95% of their customers. So what Comcast did was it deployed this technology which would detect that there was a BitTorrent connection going on, a TCP connection for BitTorrent, and then would generate what's called a reset packet. And when we talk about TCP, we'll talk in more detail about exactly what this is, but essentially it would forge a packet and tell your BitTorrent client to shut down the connection, that the transfer is done. And so BitTorrent would start up, it would start trying to send some data, and then these devices deployed in the network by Comcast would shut down the BitTorrent connections. And the reason this became very political was that this is at the same time that Comcast was starting to roll out its own video streaming service. So people were using BitTorrent to exchange movies, in some cases legally, in some cases probably illegally. And this was then seen as, aha, Comcast is claiming that it's just trying to protect its network, but it's also not allowing people to use an alternative service. It's forcing people to use their video streaming service. And this is what made the debate very political about the conflicting, sort of the you could say a conflict of interest on Comcast's part, etc. So since then, people have figured out now the IETF is working on making BitTorrent not kill connections, etc. But it was this point where Comcast started shutting down BitTorrent only, even for people who are using it for perfectly valid and legal uses. This question as to whether an ISP could decide, you can't run this application.